Alright, so last time we were working on getting the analysis working, I believe, and I realized that I had overlooked, I was writing up documentation for what we have so far, and I realized that we had overlooked some important corner case with the first and follow sets. Let's see if I can't remember where it was. Oh, I don't even remember where it was. And it's fine. We're just going to go ahead and leave it then. Test first too. But yeah, I guess just for the purposes of disclosure, we had in analysis.rs, I believe it was this if statement here we had forgotten. And so just know that there was a small oversight in the algorithm. I added a test case that would catch that, and we will leave it there. Didn't actually add any of my stuff. Let's go ahead and add analysis, grammar, lib, and tests. With the exception that I do want to get reset. See lib, get add src lib-p. Let's not add L1 yet. I guess that reset everything, that's fine. So add comments, add dot comments. What else do we have? Head is nullable seek is what is it called? First seek. So yeah, during the work that I was doing off the stream, we had a couple of so I added comments everywhere, and there were a couple of helper functions that were proving to be useful for the L1 parser table, which is taking the first of a sequence and asking if a sequence is nullable. So a sequence is nullable exactly if it contains only nullable non-terminals, and the first seek will iterate over a sequence of symbols and construct the first set for not just a single non-terminal symbol, but for an entire string. So if it starts off with a terminal, then it will return a singleton set with that terminal in it, and otherwise it will draw the first set of the symbol of the non-terminal that it runs into, and if that non-terminal is nullable, then it will go on and accumulate the firsts of all the symbols in sequence until it runs into something that is not nullable or a terminal equivalently. And so I had also been working on the start of an L1 machine. We won't go too much into this. It's still a work in progress at this moment. But there is one thing that I ran into, which is a matter of where I'm trying to take the design of this thing. And the summary of that change that I want to make is essentially that all presentations of grammars that you would see in a college textbook, including the Dragon book or wherever else, they always have this tendency to assume, let's write an expression grammar really quick, and then I'll explain what I'm talking about here. They might have it where you start off with a nice concise little grammar. That does whatever. We'll say that in this case it's going to be a little expression grammar. And they will add in a synthetic symbol called a start symbol. And the start symbol, usually it's donated with S or like E tick or something like that. But they always create a synthetic start symbol and end the production with a synthetic end of string symbol, usually denoted with a $sign here. And this kind of bugs me for two reasons. Is that on the one hand, the end of string symbol is something, it feels like a relic of the age that these algorithms were first drafted up, where they didn't have a strong understanding of how types worked in programming. And so I guess the summary of this is that when you have an input, the input to your machine is going to be some kind of an iterator where the items, this is the Rust notation for it, where the items are symbols. In my case, tick-G, whatever, just to be particular about it. So an input is going to be an iterator, and then you're going to say something like, I don't know, like dine iterator or whatever it would be. We don't care about exactly being 100% correct here, but you do input.next, and that is going to return a value that is going to be of type option symbol. What am I typing here? And so this option is going to give you all the symbols in the form of some lowercase s symbol, or it's going to give you a none. And this none is an extra element being added to, effectively, to the set of all the symbols. And none is the same thing as the $sign up here. So the $sign in my formulation of how this works, based on sort of my sense of aesthetics for how these sorts of mathematical formulations should work, is that the $sign is not actually a symbol itself. The $sign is a synthetic, is sort of a mirage created by the fact that when you do parsing, you will eventually hit the end of the stream, and that is, the end is actually represented by the noneness of it. Otherwise, you end up with this like small bit of redundancy, which in practice doesn't really hurt anything, but I don't like that, so I don't want that to be part of our analysis here. The more important thing is that the starting symbol is considered to be fixed in part of the grammar, and what that makes it hard to do is, if you want to have maximum flexibility, it may be that in some contexts, in this case we're parsing an expression, but you may imagine a grammar where S is actually going to parse a whole program, and then it has to parse the entire program. And I don't know, a program is going to be a sequence of declarations, and then go down from there. Maybe I don't want to parse the whole program. Maybe there are certain situations where I'm writing something like a read eval print loop or a REPL, where I just want to parse expressions or statements, and I don't actually want to parse the entirety of a program. But by doing this, you end up having the grammar for the language that you want, but then you also have to augment it with the start symbol. It's just something I'm trying to avoid. And so the consequence of not having the start symbol and not having the end of file symbol is that I do not include there's two parts to it. When I calculate the first set of a non-terminal, you're going to have a whole bunch of terminals in here. I never put epsilon in here, because epsilon, again, it's a synthetic thing. It's sort of a it has the same effect, but it kind of breaks the type system. Epsilon is not actually a symbol. If I want the first set to be a set of terminals, even a set of symbols, that like epsilon is not a symbol, epsilon is a string. It is the empty string of symbols, and so that can't be added. But then the other consequence is that when I calculate the follow set of a non-terminal, it can't, it can have whatever it has in there, but it can't have an EOF because it doesn't make any sense to include the end of file marker as a token, because again, there is no such thing. In the case of first having epsilon in here, I circumvent this by defining, and again, in kind of a non-standard way. This is, I have a predicate. I call this nullable, and this is the inside of the analysis. This is the isNullable function or method on the analysis class, and you just give it a symbol and it'll tell you whether or not in the traditional formulation of these things, if epsilon would have been included in first. This is just a Boolean. But I haven't really worked out an analog for what the follow set means, and part of that is that I didn't need it for what I was originally working on. In my original kind of sketch of this library, in my initial prototype, it didn't come up because it didn't come up. It was just something that I didn't need to worry about. But for doing the LR parsing, it's something where I do want to try and resolve this right now. And again, without going into details of how this works, this is a grammar. It's formulated a little bit more awkwardly than I want it to. I guess not awkwardly, but it's a different formulation than what I'm used to. I don't really care for it because it doesn't actually, makes use of these e-ticks, t-ticks, and these things are suffixes or whatever. Or this is the example here where you have a plus t. So an expression, e-tick would be like an expression suffix, and what it's trying to say is you can kind of add on as many plus t e-ticks as you want onto an e. Again, I can't even really formulate it, but it's a way of just having it so that you can have as many pluses in a row, and maybe it's not so bad, but anyway, this is not the best presentation that I want. So I have these three rules, and these represent the synthetic start symbol, the synthetic end of sequence or end of input tokens, and define EOF token, whatever you want to call it, the dollar symbol, and then the rule for those. And I want to have it so that I can get rid of these. Just to show what this is doing, we can run our I just call this test foo. So we can see what the machine did, and we don't need, again, just skipping over the details. This is the L1 parse table that we've created from the grammar that I wrote up in the test. And we can see it starts off with the initial production rule, and it's going to consider the inputs, the particular inputs that it is working with. In this example is ID plus ID times ID. And so our hope is that that would eventually give us something where, how does this work? Is this F tick, and then I think these two become an F, and then that becomes a T, and then this becomes an E or something like that. So the exact parse table, I'm not so sure. I'm not so concerned with it at this moment. I haven't gotten that far in the implementation yet. But what I have done is thrown the dollar symbol at the end of the input here, so that when you get to the end, you can see that it's considering the synthetic end of file token and the E prime, and then finally it'll pop everything off the stack and the machine stops and it passes, it accepts the input. But what I instead want to do is be able to get rid of these synthetic tokens, and then when I do the parsing, we don't need that token, we don't start with S, we want to just parse an expression. So here's the machine. The machine is going to take the parse table, which I generated above, don't worry about it. We're going to try and, the start symbol is an expression, it's an E. So we're going to parse the input, defined up here, as an expression. And again, just going back a second, I had originally had it so that there was a synthetic EOF, and we're starting with the synthetic start non-terminal S. We're going to get rid of that. But when we do that, we're going to run into issues, which is the machine runs as normal up until it gets to the point where it has run out of input. Let's see if we can't throw together a visualization of what's actually happening here. So we're going to start with our stack. Our stack is going to grow this way. It's going to start with the starting symbol here. We've got our input starting here, and we are going to trace using the table that I pre-generated. Again, the details of how that was generated are unimportant for now. We will get to that in another video after I've kind of worked things out. But the general rule is we take our input and we look at the top of the stack. I'm going to actually rearrange things just a little bit down here. I don't need these to be quite so big. So we start EID. E and ID, we're going to push, we're going to pop off our E here. Okay, we're going to pop off our E. And we're going to push T and E prime, and the order for that is, I think E prime goes on the bottom, T goes on top. Okay, then we just iterate. We see ID and T. We see ID and T, and so we're going to pop T off the stack, and we're going to push F and T prime. So pop T off the stack. We're going to get F and T prime. And then we're going to look at F and ID. F and ID, we're going to pop F off the stack, and we're going to push an ID. And then because the top of the stack and the first element of the input match, we're going to pop that off. We're going to take this, and we have successfully parsed the ID. We're going to move our input over to the plus sign. And from there, what we're going to get is T prime and plus sign is going to be such that, that T prime, we're going to pop that off the stack and just delete it because the right-hand side is empty here. Then we're going to take that E prime and the plus symbol, E prime plus symbol, we're going to take that and we're going to pop off E prime and push plus T and E prime in reverse order. So we're going to take the E prime, we're going to pop this E prime off, push a new E prime on T, and plus go on the stack. The top two match. So we're going to take our plus and accept that into our final results. We're going to take the ID and the T. We're going to pop off that T and put FT prime. So FT prime. We're going to take F and ID. F and ID means we're going to take off the F. And we're going to push ID onto the stack. We see ID and ID. So that means that we're going to match, and we're going to take that ID. We're going to push it over to our accepted input. And we're going to shove the pointer over one more. We've got star and T prime, star and T prime. Where is T prime? Where is star? We're going to pop off T prime and put star F T prime. So we'll put star F and a different copy of T prime. The top two match. So we're going to take that star, get rid of that one. We're going to push this over here. We're going to move the cursor over here. We have F and ID. We're going to pop off F according to this rule. We're going to replace the F with the ID. We're going to see that there's a match. And so we take our ID and accept it. And so we are at the end of our input. However, we don't have an empty stack at this point. We have T prime and E prime remaining on the stack. And so over here, T prime and E prime, we see that the E prime and T prime both have rules according to our grammar such that they this isn't the same as up here. I don't know why I have this distracting grammar up here, but you can kind of see the grammar that I do have in here, that both E prime and T prime have rules that end in a null production, that these both should have rules that say when T prime is faced with an empty input, then you can accept it. But and maybe that's all I need to do for this. Maybe I don't actually need to know whether or not it can match the end of input or not. Because what happened here is, you can imagine a recursive descent parser where you have a parse rule for like parse E, which is a function, a parse rule for parse E prime, a parse rule for T, a parse rule for T prime, and a parse rule for F. And these are functions. So E is going to call E prime is going to call E prime is going to call T. E can also call T, I guess. I guess that can also happen. And hopefully I'm not messing this up too badly. And then it's mutually recursive, so at the very bottom, F can actually call E as well. So here we've got a case where when we call E with the input that we had, we're actually descended pretty far down the call stack on this final parse F. Parse F is going to consume the final ID token, and it's going to succeed as a parser, but then it still needs to yield control. It has to do a bunch of return. I mean, it's going to return to TP. TP is going to return to T. I guess in this case, the actual call stack is not quite like that, whereas the actual call stack is going to look like this, I believe. Yeah, so we are in F because we just popped F off the stack. We came from T prime and we came from E prime. So we're at the end of the function. We've done all the work. We just need to return at this point. And the trouble is knowing that you're allowed to return from these things. We need to add rules over here that basically say when E, and it's hard to know exactly how this is represented because this isn't actually a token. This is a case of this is a case where what's actually being represented here is an optional token. So there can be an extra slot here with EOF. maybe what I actually want to do is say, when I'm building this table, we're going through each rule. If the left-hand side is nullable, just copy some of this boilerplate over here, then we're allowed to say, I guess, yeah, we're allowed to return with the rule at hand. There is a rule in scope there. So the problem that you run into, this would require more explanation than I can probably really give. Well, let's try the actual parse table that we've generated here. Or yeah, the parse table looks like this. And let me just comment this out. So, and let me get the grammar too, as long as we're here. So the grammar is going to be E goes to T E prime. And then E prime goes to either plus T E prime, or E prime can be empty. And we have T. T can go to Ft prime. And T prime similarly can be a sequence of multiplications against various factors, or T prime can be empty. And then finally, F can either be sort of our base case ID, or F can be open parenthesis, E close parenthesis. So this is our grammar that we're working with. And so our parse table is going to be a table where the rows are the various non-terminals. So that's going to be E, E prime, T, T prime, F. And then along the top, we're going to have our non-terminals, which are going to be ID plus times open parenthesis, close parenthesis, and also the end of input here. I'm going to number my rules here. So this is rule 1, rule 2, rule 3, rule 4, rule 5, rule 6, rule 7, and rule 8. And I'm going to make my table a little bit nicer to read, moving things over. Well, I guess this is as good as a time as any to explain how the table is actually constructed. Is we look at each rule in turn. So for rule number 1, we're going to take the first of the right-hand side. This is actually a new function that I added as a helper in the analysis, which is the first of the sequence, t e prime. So this is new, and it's not just the first of a non-terminal, but rather the first of a sequence, and it has special mechanics where if the first thing is nullable, then it actually unions the first with the thing following it, and so on here. But intuitively, the first of t is going to be, or the first of t e prime, t is not nullable, and so that's just going to be the first of t. And the first of t is going to be the first of f, which is also not nullable. So the first of this sequence here is going to be either id or the open parenthesis. And what we do is, this is kind of this token up here is considered to be the token that we're currently peeking at from the input, and this is the thing that we're trying to parse. And so if we see ID or open parentheses, we actually use rule number 1, because that was the right hand side here. This is what rule number 1 will always start off. Ultimately it has to expand where this t turns into an ID or an open parenthesis, and it has to be one of those two. And so you have to apply rule 1 when you see an ID or when you see an open parenthesis. And we're going to go down the line like that. So the second production rule that we have is this plus t e prime on the right hand side. We're going to take the first again of that sequence and figure out what to do about e prime here. So in the case, because this starts off with a non-terminal, it always has to be the plus symbol. So for e prime, when you see the plus symbol, you have to apply rule number 2 to it. The next one is where things get a little dicey. So for rule number 3, we're taking the first of the right-hand side of rule 3, which is the first of epsilon. And you're like, well, you keep saying this epsilon thing isn't a symbol. Well, this is a sequence, so this is really saying the empty sequence here. You kind of just say first of empty, but it's, again, it's like a list with 0 elements, and you're the first of an empty string, of the empty string is defined, and it makes total sense within the framework that we're working with. The first of the empty string is going to be an empty set, because if you have an empty string, there can't be any terminal at the start of that, and so no answer is going to give you the correct answer, therefore the set has to be empty. The problem with this is that in this circumstance, it's not that rule 3 doesn't get used, it's that for e prime, because again, that's the left-hand side, when the first set is empty, that, I think it has to go here. The tricky thing is, so we're going to put that rule number 3 underneath the dollar, again, lined up here. The tricky part of this is that depending on how I write things, I might be able to make a slightly more general system, because you can imagine something where maybe there's some a that goes to epsilon, and this E prime actually goes to A. And so that, maybe it doesn't make so much of a difference. We have, so E doesn't, the first of A in this case, it's kind of a stupid grammar because this production rule is not just nullable, but it's a nullable with a null first set, and so that would give us an empty set as well, and the same thing would apply as you just apply this rule. But you actually have to apply this rule first. So this puts a constraint on the kinds of grammars that we're allowed to work with. There's already a fair number of grammars that are restrictions on LL1 grammars. They have to be free of left recursion. I don't know exactly what it means, but they have to be, I think left factored is the other condition that's normally stated, which means that whatever, there can't be two rules that have the same first set. And in this case, I guess that's the real issue here. I don't know. In any case, like there's some precondition under which like the grammar will fail, and I don't know if this is a standard one or not. We're just going to go ahead and ignore that fact. And so if we're going to make the case that make the decision that if we do find the right hand side has an empty first set, then we apply that rule for the right hand side combined with the end of input. So let's go ahead and write that and encode that. So what is this going to say? Is nullable sequence. Oh, so here's where the trouble comes in, is the way that there's one other. Does this actually take care of if the sequence is totally nullable? Then you have to add the rule for all of the follows. I don't think that's the case for anything that we run into here. If the sequence is nullable, and here it's just I have to go into a very provy way of thinking about things. If the sequence is nullable on the right hand side, then normally what the standard textbook definitions, the textbook advice is that you should add the rule to everything in the follow set. And the problem here, we come around to the issue that I ran into, is that the follow set of the left-hand side the follow set here would be the follow of E prime, which, how does this actually look? Would be the follow of E prime would be the follow of E. Because it's at the end of this sequence here. I think that's the case. The follow of. So what's the follow of E would be close parenthesis. But the problem here is that the follow of E is actually not, well, the standard textbook presentation says that the follow of E should also contain the dollar synthetic symbol. And why is that? It's because if follow of E was only the closed parentheses, that would say that whenever you have an E prime, you always have to have a closed parenthesis, but that's not the case. The counterexample to that would be something like ID plus ID. And here, the plus ID, this turns into, like, if we actually create the proper parse tree on this, let's do that. So here is our sequence. We're going to take E, it's going to go to TE prime. The T is going to go to FT prime. This T prime goes to empty because there's nothing we need. That F will go to ID. This E prime will go to plus T E prime. This E prime goes to empty. This T goes to, this is such an obnoxious, useless grammar. FT prime. This T prime goes to epsilon, and this F goes to ID. Oh, that's rough. So, so this would be our parse tree. We get a lot of these dead ends that we don't like, but they're still part. So the problem here is that we say that this E prime, what is following the E prime? Because the follow of E prime is this closed parenthesis, we would imagine that there has to be a closing parenthesis, but the way that we've written this, the way that we're formulating things, is that if it's followed by anything, it has to be followed by a closed parenthesis. But in this case, it's not, because it's the end. It's a node on the. If you descend across the final, the right hand side, and just do straight down the right, you go the sequence E, E prime, epsilon. All of these symbols are special designated symbols for, or I guess the non-terminals, let's say. These three I guess there's only two of them because the E prime is circled twice, but these non-terminals are a special class, and they are things that can end. Oh, a T cannot appear in this position. If you start with E at the top, if you start with E at the top of your parse tree, you will never see a T in this position. You will always see an E prime. Maybe you can see a T prime? Maybe? No, I don't think you can even see a T prime. So there's a special relationship between E and E prime here, which is saying that that E prime can terminate E, that it can be sort of the last. If E is the first symbol, E prime can be a last symbol as well. That there is nothing following it. And similarly, you'd have a reflexive relation. It would be a reflexive relation between non-terminals such that any symbol will terminate itself. But E prime can terminate E. And I think that's the case that we need to consider. Is not ask if it's null, if the right-hand side is nullable, but rather, can the right-hand side terminate the start symbol? And so my thought is that adding this as something in the analysis can end with is the best name that I could come up with. The word terminate is not the best because it's too similar to terminal. Can end with we'll namesmith it later, but the general idea here is that we're going to look at the production rules and see the last symbol. The thing is that E prime can also be emptyable, but when that happens, what's important... Oh, no, 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 no. Yeah, so my analysis here is a little bit off because the T and T prime are kind of sensitive to what I'm trying to convey here, is that when we start with E, all of these symbols, all of these non-terminals are non-terminals which can appear at the end, essentially at the end of the parse. So anything to the right of them not just right, but like, I guess it is to the right. Yeah, so maybe we want to draw this a little bit cleaner. Let's get rid of this parse table that we've drawn up here because we don't need it. So, starting with E, let's actually do this. We're going to read off all of these leaves, but we're actually going to put these empty string symbols here as well. We can insert them or remove them at will. Let's get that centered a little bit. Give us lots of space. We're going to say this E prime no, maybe we'll do it like this. We'll stagger it. I don't know. We'll just do the tree like this. Well, I'm not sure exactly how I want to do this. Is it... no worries. We're just going to do this. E prime here. T here. And this turns into F, which gives us the ID. This gives us a T prime, which gives us an epsilon. This E prime then turns into this plus sign here and a T. The T is going to give us an F and a T prime. And the T prime will be this epsilon, and the E will give rise to an E prime. Okay, maybe this is a little bit better. What I care about here is that this is the final token. These aren't actually tokens. And so I want to see what things can consume the final token. This E prime doesn't consume a final token. So these things are going to be making use of the fact that they are nullable to expand to nothing. So the things that are actually nullable are the t prime and the e prime using these two rules. And so f, t, e prime, and e are all things that can consume the final term or the final token. Let's take a look. If we look at the rules, so if E is our starting rule, then we have a bunch of stuff and it ends with E prime. So presumably E prime can appear at the end if it's not totally degenerate and it's just a nullable, just doesn't actually produce anything at all. That case makes it more difficult to do the analysis. But that's not the case here. I guess but consuming the final token isn't the same thing as, again, maybe we just want to imagine for a second that we have a rule 0 here with a start production that takes whatever that is and adds a $sign. And the question here is then, an equivalent question then using this grammar is the follow of what symbols of which non-terminals is a $sign or includes the $sign. How do we calculate the follow again? You have to know the firsts and follows. Is there anything that can actually be... The follow is a terminal. We're going to go through each of the rules and play this game where we're looking for non-terminals such that when we circle them and the next one over is a terminal. So So I guess the sort of obvious the obvious place to start with this is actually that follow of the thing designated as the start rule will always contain that. And that's our base case. So follow. So we get sort of this, but that's not quite everything here. We'll never actually be able to make use of this rule because the $sign will never actually be a first. So maybe, well, the first, nothing. First of n never contains for any n. I guess for all n. Nothing can ever start with the end because it's only added in the one place. the start rule. I guess there's only a degenerate case again where this is actually an important case because a lot of times the thing that you're trying to parse would be like an empty program. So let's ignore that as a manageable corner case. What we want to do is then so we're going to just daisy chain follows together. So follow of E, anything that points to the follow of E inside the graph. I guess that makes sense, right? Anything that points to the follow of E. Terminals from. And we'll just put a suggestive name here of start symbol. I think I have the general strategy here. I don't know if I have the fortitude to go through and do this at this moment, so maybe we'll leave this here for now and we will try this again another night. But we're getting closer. Just to put a to-do in here. Self dot first follows dot follows to follows start symbol contains symbol. This is going to create a bunch of recomputation. I don't care. We're going to leave it for now, and we can finish this up and do the graph math in another video. So thank you.